Hello everyone and welcome to this video. Today we're discussing the part 2 in the chapter Electrostatics, and specifically we're talking about the electrostatic potential and potential energy. Now previously we have discussed the concept of the electric field. The electric field concept is very important and extremely useful and can be used to solve a large number of electrostatic problems. However, because the quantity of the electric field is a vector, it becomes really difficult to deal with the quantity E in all the formulae that we have seen before. Also, the integrals in the formulae, like the one in Coulomb's law, gets complicated really fast. To solve some of these problems, what we do is come up with a new concept, that is the concept of the electrostatic potential. So you have to remember two things. One, the electrostatic potential is a scalar quantity as opposed to the electric field, which was a vector quantity. And therefore, right away, our job is made one step easier. Secondly, you also have to remember that now we are going to look at the same electrostatic field from the perspective of the electrostatic potential. We are going to look at some of the same cases that we saw previously, but now we are going to try to look at them from the view of the electrostatic potential. So let's start. Now the word potential itself is not a new word. We have heard of the word potential and potential energy before. And we have heard this in case of the gravitational field. And similar to the gravitational potential energy, we will define what is known as the electrostatic potential energy. In case of the gravitational potential energy, we saw that every object which is at some distance from the center of the earth, this object possesses a gravitational potential energy because it is at some distance d from the center of the earth. In this case, we had two masses m1 and m2 separated by a distance d, and because of their separation, these objects possess gravitational potential energy. Similarly, there is also the concept of the electrostatic potential energy in the field of electrostatics. Here you can see, instead of the two masses, we have two charges separated by a distance d. In gravitation, you had the gravitational force which was acting towards each other because the gravitational force is always attractive. However, the electrostatic force can be attractive or repulsive. In this case, because both the charges are positive, it will be repulsive, but if the charges are opposite, it can also be attractive. But you can see that the gravitational potential energy and the electrostatic potential energy are analogous concepts. Just like you define the gravitational potential energy, you can define the electrostatic potential energy. So we say that whenever one charge is taken at some distance with respect to some other charge, that charge will possess electrostatic potential energy. Now that we have created some kind of connection, let's see how to define the electrostatic potential energy. Let's say that you have some charge Q placed at the origin. This charge is capital Q, and we know that a charge produces an electric field in the space surrounding it. And therefore, if I try to bring a small test charge, small q, and I try to bring this charge close to this capital Q charge, then in that case, I know that this capital Q will exert a force of repulsion towards this small charge Q. So we know that there is going to be a force of repulsion experienced by this small test charge Q. Now remember, this charge that I am bringing, that is the small charge Q, is very small as compared to the charge which is creating the electric field, that is as compared to capital Q. Okay, what am I trying to say? I'm trying to say that when you try to bring this small charge close to this bigger charge, we know that this small charge will experience a force of repulsion. And this force of repulsion is created because of the force exerted by the electric field, that is Fe. So which means that if I want to bring this charge small q closer towards the bigger charge capital Q, to just bring it closer, I will have to give an external force, and this force will be equal and opposite to the force exerted by capital Q. And only when you give an equal and opposite force will you be able to counter this repulsion and bring this charge closer and closer to capital Q. Once you do this, you will see that when you bring this charge closer and closer to the capital Q charge, what is happening is that you have to do work. Applying external force means you are doing some work to bring this charge from point P to point S. And this work done, that is the work that you had to do, that means the work by the external force which had to be done on this small charge just to bring it from P to S, will be negative of the work done by the repulsive force, because these forces are equal and opposite. Let's see if we can write this mathematically. We know that work done is nothing but the integral of force into displacement. And we also saw that Fe is nothing but minus F external. So I say that the work done by external force in moving a charge q from P to S is given by this formula. As you can see, work done's formula is written. We have said that it is the integral of the external force into the displacement caused by it, and instead of external force I have written minus Fe, that is minus times the repulsive force exerted by the electric field itself. So we get the formula for work done in bringing a charge from point P to point S, that is minus integral P to S Fe dot dr. Now we're ready to define the electrostatic potential energy. I'm saying that because you had to do work in bringing this charge from some further point to another point closer to the capital Q charge, because you had to do some work, this work was done on the small q charge and got stored in that charge in the form of electrostatic potential energy. So the work done against the electrostatic repulsive force got stored in this small q charge as potential energy. Think of it as pressing a spring. As you press the spring closer and closer and closer, you'll see that the energy gets stored in the spring, so that as you release, the spring will just go back in a flash, similar to the charge, that if you don't apply the external force, the charge will just get released back to a point where the electric field cannot reach it. So that's why I say that when you bring this small charge closer and closer and closer towards the capital Q, you are doing work, and this gets stored inside this small q as potential energy. Now this means that every time you bring a charge inside an electric field, at that point the charge will possess potential energy. And therefore I say that the point P where the charge started from will have some potential energy UP, and similarly where the charge reached, that is the point S, will also have some potential energy US. Remember, these values of the potential energy are coming about because of the capital Q. If this capital Q was not sitting there, then these points would not have any electrostatic potential energy. So we say at point P there is some electrostatic potential energy, that is UP. At point S there is some electrostatic potential energy, that is US. And when you brought this charge from P to S, you did work, and we say that this work done is stored as electrostatic potential energy. In fact, the potential energy difference is given as the work done. So you can see that the work done in bringing the charge from P to S is written as delta U, that is US minus UP. So the work done in bringing the charge from one point to another is equal to the potential energy difference between the 2 points. So finally, we can define the electrostatic potential energy difference. That is, it is the work done by an external force in moving a charge from one point to another of the electric field for any charge configuration. Finally, remember one important convention about the potential energy. We assume that the potential energy at infinity is 0. And therefore, instead of bringing the charge from some point P to S, suppose I bring the charge from infinity to S. Then in our previous formula, basically what will happen is that WPS will become W infinity S, because now the charge is coming from infinity instead of P. And therefore, I will get US minus U infinity. But I just told you that the potential energy, that is U infinity, at infinity is taken to be 0. So U infinity becomes 0, and I get that W infinity S is equal to US. This defines the electrostatic potential energy at a particular point. Previously, we defined the potential energy difference between 2 points. Here, I am defining the potential energy at a single point. So the potential energy at a single point, the point S, is nothing but the work done in bringing a charge from infinity to this point S. As you can see from the formula, W infinity to S is equal to US. So US is the potential energy at a single point S. Finally, we learn one other property about the electrostatic potential energy. The electrostatic potential energy is conservative. Now, what does this mean? If you have a capital Q charge, we know that this charge will create an electric field in the space surrounding it. And every time you try to bring a charge at any point in this field, this charge will possess electrostatic potential energy. Let's say, for example, you bring a charge from infinity and you keep it at point R. This point, that is the charge's location, this point will have electrostatic potential energy UR. When I take it to a different point, it will have electrostatic potential energy US, and so on and so forth. So as you can see, every point possesses an electrostatic potential energy, and as I brought the charge from infinity to R, to S, to T, to W, finally I see that the charge has attained an electrostatic potential energy of UW. But here I have taken a very specific path. I brought it along this straight line from infinity to this point W. But this is not necessary. The potential energy is conservative, which means it is path independent, which means that instead of bringing this charge from infinity in some perfectly nice straight line, if I had brought it randomly from any direction and placed it at the point W, then because the initial point, that is infinity, and the final point W are the same, the potential energy that this charge will have will still be UW. And therefore I say that the electrostatic force is a conservative force and the potential energy is path independent. That is, you can bring the charge from anywhere to any point, but as long as the initial and final points remain the same, the path does not matter. The value of the electrostatic potential energy at that point will not change. So we say that the work done by the electrostatic field and hence the potential energy difference depends only on the initial and final points and is independent of the path taken to go from one point to the other. Thus, the electrostatic force is a conservative force. From electrostatic potential energy, we can define what is known as the electrostatic potential. But the question is, why do we have to define it at all? This is because the definition of the potential energy included the value of the charge which we are testing. We said that the electrostatic potential energy is work done per unit charge. So I wanted to define something, that is, I want a quantity which does not depend on how much charge I am placing at a point, and therefore we define electrostatic potential. This is because it is independent of charge. So if I'm saying it is independent of charge, this means that what I'm going to do is I'm going to take the formula for the electrostatic potential energy and simply divide it by the amount of charge to get me the quantity, that is electrostatic potential. So I say that you divide the work by the amount of charge Q so that the resulting quantity is independent of Q. And this quantity which is independent of Q is the electrostatic potential. And because this quantity is independent of Q, which means it is independent of how much charge you put at a point, it means that the electrostatic potential will be measured to be the same by anybody, independent of how much charge you put. And it also means that this is therefore a characteristic of the electric field, which means that this is a property of the field itself. It does not change by how much charge you put at a point when you are measuring the electrostatic potential of a point. So, from this we can understand that the electrostatic potential is a more important quantity, slightly more important quantity than the electrostatic potential energy, because the electrostatic potential does not depend upon the charge, that is the test charge which you will put at a point. Okay, so like I said, we have found the electrostatic potential only by dividing the electrostatic potential energy by the charge Q, and therefore the definition will be the same, but we will say instead of taking charge, we will say we have taken a unit charge, because it is nothing but per unit charge that we have defined the electrostatic potential. So we'll take the same definition, that is electrostatic potential is the work done by the external force in bringing a unit positive charge. There it was just bringing a charge. Here I am saying it's a unit charge from one point to another. And there we found the formula, that is, we said it is the work done to bring the charge from a point P to a point S. Here I am saying it is the work done per unit charge, because here, like I have said before, I divided it by small q. So now you see electrostatic potential difference is work done by Q, which is what I've said, we've divided it by Q, and this is nothing but the change in potential energy. We've already seen work done is change in potential energy, so I've written US minus UP, but here I have divided it by Q to get the electrostatic potential. So US minus UP upon Q will be given to be Vs minus Vp, where Vs and Vp will be the electrostatic potentials at P and S respectively. So actually what we have found here is the electrostatic potential difference, which means that if I want to define the electrostatic potential at a single point, I will do the same thing that I did before. Before, when we had to find the electrostatic potential energy at a single point, I said bring it from infinity to that point, and the electrostatic potential energy at infinity I wrote as 0. I'm going to do the same thing here. I'm going to say you choose the point at infinity to have a 0 potential, and then I define the electrostatic potential at a single point to be such that it is the work done by an external force in bringing a unit positive charge from infinity to that point. And this is the definition of the electrostatic potential at that point. So remember, we got electrostatic potential by the electrostatic potential energy. We simply just divided by Q. The only difference is there we were bringing the charge from infinity to a particular point, or we were bringing it from one point to another, but we were bringing a charge. Here we are bringing a unit positive charge. We are always bringing a unit positive charge. So this is the definition of the electrostatic potential. And using this definition of the electrostatic potential, now I can find the potential due to different such charge configurations. For example, if I have a single charge, that is, I have a point charge, let me ask what is the potential due to this single point charge. So I say I want to find the potential at any point P due to a single point charge. So please pay attention to the title. We are saying that we have to find the potential at a particular point due to a point charge, which means this point charge is already there at the origin. For example, we have placed it at the origin for convenience. This point charge is already there and I want to find the potential at some other point due to this point charge. So to do that, we have just learned that the electrostatic potential at any point is work done per unit charge, which means first I have to find out what is the work done in bringing a unit positive charge from infinity to some point, because I want to find the electrostatic potential at some point. Let's say I want to find the electrostatic potential at a point P, which is at a distance of r from this point charge. So if I want to find the electrostatic potential at this point P, then by definition what do I have to do? I have to find the work done in bringing this charge from infinity to this point P, and that will be the electrostatic potential at this point. So when I'm trying to bring the unit positive charge from infinity to a point P at some intermediate point, let's say that point is R, in some point in between which is R, where the distance from the point charge is R dash, when I'm bringing this charge from infinity to P, we will stop at some point R. Let's say that it has reached this point in between R, which is at a distance of R dash from the point charge. At this point, what is going to happen? We're just basically observing a random point. While it is coming from infinity to this point P, I'm just looking at some random point in between. And this random point R, at this random point, what's going to happen is that this incoming charge, this unit positive charge which we are bringing, is going to face some kind of repulsion from this point charge Q. And this repulsion will be given by the Coulomb force. And it will be nothing but capital Q into 1 upon 4 pi epsilon naught R dash square. So why is there a 1 there? 1 is because what I'm bringing is a unit positive charge, right? To find electrostatic potential, we are bringing a unit positive charge. That's why we have 1. Capital Q is the charge of this point charge, and R dash is the distance between their centers. So as we have seen, this is the Coulomb's law, and I found the repulsive force which is acting on this charge as I am bringing it from infinity to P. And like I said, I am observing this random point in between. So when I am observing it, I see that this amount of force is acting at this point. Now I will bring this charge closer to the point charge by some distance. I say that this distance is delta R dash, and I am bringing it closer against the repulsive force of the point charge. So I have to give an external force. That's what I'm doing, right? I'm bringing it, which means I am the external force. So I bring it from point R closer to the point P, and I bring it by a distance delta R dash. As I have brought the point closer towards the point charge, therefore the work done is against the force of the point charge, that is the force of repulsion due to the point charge, and this work done is, and you dot that with the displacement, and the displacement is delta R dash, but because it is closer, that is, it is coming towards the point charge, it is a minus sign. So you see that the work done, that is delta W, is minus Q upon 4 pi epsilon naught R dash square into delta R dash. Finally, if I want to find the total amount of work done, what I will do is I will integrate this expression from infinity to R, because final destination is the point P, which is at a distance R, and the initial destination is infinity, which is at a distance infinity. That means I am integrating minus 1 upon R dash square, which will become 1 upon R dash, and I will put the limits, that is infinity and R, and because 1 upon infinity is 0, I get that the work done is Q upon 4 pi epsilon naught R. And this is the expression that I want. I have found the potential at some point P due to the point charge capital Q, which will be given by capital Q upon 4 pi epsilon naught R, where R is the distance of the point P from the point charge. So I have found the expression for the potential due to a point charge. This tells me something very, very important. From Coulomb's law, I can tell that the electrostatic field is proportional to 1 by R square, but from this expression, I can see that the electrostatic potential, it is inversely proportional to 1 by R, and therefore electrostatic potential falls off slower than the electrostatic field, and this is extremely important to know. With the expression of the potential due to a single point charge, I can now find the potential due to an electric dipole. But I want you to see carefully what we are doing. We have already seen these charge configurations previously. We first dealt with the point charge, and we dealt with the dipole, and then we went to systems of charges. But in those cases, we were always trying to find the electrostatic field. In these cases, here we are trying to find the electrostatic potential. So we are just doing the same exercise, but from the point of view of the potential. So let's try to find the potential due to an electric dipole. By now you know an electric dipole is nothing but two opposite charges placed at some distance. Here we call that distance 2a, and O is the center of the dipole. The electric dipole is a vector that is pointed from the negative towards the positive charge. So what I want to do, I want to find out the potential due to this electric dipole. At which point am I going to try to find the potential? We are going to first look at the case where there is some random point. We are going to look at a random point P anywhere in the field of the electric dipole, and this random point P is where we want to find the potential due to this electric dipole. So we are going to name some conventions. We are going to say that let the position vector of the point P as respect to the positive charge be R1, and the position vector from the negative charge to point P be R2, and the vector from the center of the electric dipole to P is said to be simply R. Also, we say that the angle between this R and the axis of the electric dipole is theta, and accordingly the other angle will be 180 minus theta. Now it's very obvious. We have defined the electrostatic potential, and what we're going to do now is use the principle of superposition. We are saying that we want to find the potential at point P due to this electric dipole. But this electric dipole is nothing but 2-point charges, and we already know the expression for potential due to a point charge. So we will apply that expression to the first charge, that is plus q, and then we'll apply that expression to the second charge, that is minus q, and we will add them up. So let's start. I want to find the potential at point P due to this electric dipole. First, I will ask what is the potential at P due to the point charge plus q. So I will get that it is 1 upon 4 pi epsilon naught q upon r1. Q because the charge is q, and r1 because that's the distance of the positive plus q from the point P. And then I will add to this the potential at P due to the negative charge, that is 1 upon 4 pi epsilon naught minus q upon r2. The minus comes because the charge itself is negative, and r2 is of course the distance between the negative charge and point P. So here I want you to notice something wonderful. This is exactly why we define the electrostatic potential. Here, as you can see, this is not a vector addition, it is a simple scalar addition, where R1 and R2 are just the distances in magnitude. And therefore, you see that the electrostatic potential has some benefit over the electrostatic field, because this is just a scalar addition. And therefore, I take 1 upon 4 pi epsilon naught outside, and I get that V is equal to Q upon 4 pi epsilon naught 1 upon R1 minus 1 upon R2, and then we put in a small approximation. This approximation is valid for short dipoles, that is, I replace 1 upon R1 minus 1 upon R2 with 2a cos theta upon R square. This is a long derivation, we won't get into it right now. This is the approximation, but remember it is valid for a short dipole, which means that R, that is the distance of P from the center of the dipole, is much greater than the size or the longitudinal extent of the dipole, that is much greater than A. So in this case, we have approximated this to 2a cos theta by r square, and we know what is the definition of the magnitude of the dipole. We know that P is 2aq, that is the distance into any one of the charge, that is the magnitude of the charge. So we can replace 2aq by P, because we know that by definition the magnitude of the dipole moment is the distance between the two charges and the multiplied by the charge on any one of them. So 2aq is simply replaced by P by definition of the electric dipole moment, and therefore I get the formula that V is equal to 1 upon 4 pi epsilon naught P cos theta upon r square, where r is the distance of the point P from the center of the dipole. So this is a formula we got for a general point P. This point could be anywhere. Now what we're going to do is replace P cos theta with the dot product P dot r cap. This is because we know that dot product is nothing but magnitude of the first vector into magnitude of the second vector into cos of the angle between them. So we replace P cos theta with P bar dot r cap, and this is just one other way of writing the electric potential due to an electric dipole at a point P. So here I can see that we have two formulae. The second one has some vectors, but overall the potential is still just a scalar. It's a dot product, right? So it's going to give us a scalar answer. So these are the two formulae, but remember we have found these formulae by assuming that the electric dipole is short, that is the length, that is the distance of the point P is very far away from the center of the dipole. Now what I can do is get some specific cases. Let's say that the point lies on the dipole axis, which means that the angle is either 0 or pi. You can simply put these angles in the equation we have just found. So instead of theta, if I write 0, then it is obvious that cos 0 is 1, and this gives me the potential as 1 upon 4 pi epsilon naught P by r square. But suppose it is 180, which is the other side. If it's 180, that is its cos pi, it will give me a minus 1, and then this will become minus 1 upon 4 pi epsilon naught P by r square. So overall I can say that a potential at a point on the dipole axis will either be plus or minus 1 upon 4 pi epsilon naught P upon r square. Similarly, I can get another specific case from the general formula, that is the potential in the equatorial plane, which means it is in the equatorial plane, and therefore the angle is 90 degrees. And if it's 90 degrees, then you will get cos 90, which is nothing but 0, and therefore the potential in the equatorial plane of any point will come out to be 0. So this is how we found the potential due to an electric dipole. Finally, what I want to do is compare the electric dipole versus a single charge. A single charge is just one charge. Electric dipole is 2-point charges separated by some distance. So from the values, that is the expressions that we have found, we can see very clearly that electric dipole was 1 upon 4 pi epsilon naught P cos theta upon r square. Single charge is just 1 upon 4 pi epsilon naught Q upon r. And so what we have noticed is that the electric dipole potential falls off at large distances as 1 upon r square. The V is proportional to 1 upon r square, but for a single charge it is proportional to 1 upon r, and this is important to note. So now I want to find the potential at a point due to a system of charges. A system of charges is nothing but many charges. For the electric dipole we had only 2 charges, but here I have 4 charges. So now I'm going to use the superposition principle. I already actually used it for the electric dipole, but I'm doing it again because I want to point out that you can use this for any number of charges. So here I want to find the potential at point P due to all these 4 charges, which will be nothing but the potential at point P due to the first charge. Let's say that's V1, which will be given by 1 upon 4 pi epsilon naught Q1 upon R1P, where R1P is the distance or the position vector between P and Q1. Similarly, I will have to find the potential at P due to the other charges. Let's say the charge Q2, Q3 and Q4. So there will be V2, V3 and V4, and in each of them you will have the same kind of expression, but the numerator will have the charge, that is Q1, Q2, Q3 or Q4, and the denominator will have the respective distance, that is either it will be R1P or R2P or R3P and R4P, depending upon which distance you're finding between the point P and which charge. So here you can see all the 4 expressions are the same. The point is that you can simply add them all up to find the potential due to this system of charges. So the final potential at a point P will simply be given by the superposition principle, which says add all these potentials up. So I get V is equal to V1 plus V2 plus V3 plus V4 plus whatever and so on. And again, I'd like to point out that the electrostatic potential has given us this equation, that is the superposition principle, and electrostatic potential has given us this equation, which is a scalar. When we wrote the superposition principle for the electric field, we had a vector equation, so we had to keep in mind of the directions and the angles, but this is a scalar equation and you simply add up this value, and therefore this is the benefit of using the electrostatic potential. So I get that V is equal to 1 upon 4 pi epsilon naught Q1 upon R1P plus Q2 upon R2P and so on and so forth. In general, it will be Qn upon Rnp. So this is how we find the potential due to a system of charges. But one thing which is important to note is that these systems of charges is a discrete system of charges, which means I can actually count on my fingers how many charges are there. Even if it's 20,000, 30,000, as long as they are separate and away from each other in some small way also, we say that they are discrete charges. That means I can differentiate. That means I can differentiate from one charge from the other. What does this mean and why am I talking about this? I'm talking about this because what will you do if you have a continuous distribution of charges? So we saw this case in the electric field sense also. And again, I'm saying that if you have a continuous distribution of charges, let's say you have this entire block which has a charge. That means now I'm talking about a continuous charge distribution, because inside this block you don't know where one charge is and the second charge is and so on and so forth. This is just an entire volume of charge. In this case, I will define a volume charge density also sometimes simply known as the charge density, that is rho. And this volume charge density will be important to find the potential at some point P, which is at a distance from this volume of charge. So now if I want to find the potential at P, what I'm going to do, I'm going to cut this volume into small elements. We've done this before and we're doing it again. You cut this volume up into small elements. Every time you see a continuous distribution, you need to cut it up. So if you have a volume charge, you have to cut it up into, that is a 3D object, you cut it up into volume elements, and then you ask what is the potential at point P due to one small element, and for this small element you will find the potential at P. Let's say this potential is V1, and you will repeat this exercise for all the other elements. Let's say in case of this cube, I repeat it for all the 9 small cubes. As you can see, you will have to add all these potentials up, and then you will have to repeat this for the second row and the third row as well, and together they will give you the potential at P, which will be just a scalar addition because of the superposition principle. It will just be an addition of the potentials due to each of these volume elements. So this is how you deal with a continuous charge distribution. From this, by using this same logical principle, I can find the value of the potential for some symmetrical shapes. One important symmetrical shape is the spherical shell. So for a uniformly charged spherical shell, the electric field outside the shell is given by the equation, that is, let's say that I have a uniformly charged spherical shell and I want to find the electrostatic potential at some point P, which is at a distance small r from the center of this shell, whose radius is capital R. Then I see that the potential outside the shell at this point P comes out to be 1 upon 4 pi epsilon naught q upon small r. But if you take a look at this carefully, this is the same expression that you've got for a point charge, and therefore we say that a uniformly charged spherical shell, if you see it from the outside, it's as if it was just a point charge located at the center of the shell. So we say that the entire charge is concentrated at the center. It's as if the entire charge is concentrated at the center. So now we see that we got the potential at a point P outside the shell as 1 upon 4 pi epsilon naught q by r, where r is simply the distance between point P and the center of the spherical shell. And now we also know that because it is a uniformly charged spherical shell, which means it's a conductor, the electric field inside this must be 0. And if the electric field inside is 0, then no work will be done in moving a charge from one point to another inside the shell. And if no work is done, it means that the potential is constant. So we say that the potential, the electrostatic potential inside a conductor, in this case inside the uniformly charged spherical shell, will be constant, and it will be equal to the value of the surface. That means instead of writing small r, I will say capital R. The potential inside this uniformly charged spherical shell is 1 upon 4 pi epsilon naught q by capital R. So for a point outside the shell, it was q by small r. For a point inside and at the surface of the shell, in both cases, I get q upon capital R. And this is an important result that we use very often. From the expressions of potential for various charge configurations, we can find what are known as equipotential surfaces. An equipotential surface is nothing but a surface on which the value of potential is constant at all points on the surface. So how will we find this? Let's go back to the expression of the single point charge. There we found that the potential due to a single point charge is 1 upon 4 pi epsilon naught q upon r. So if you look at this expression carefully, 4 pi and epsilon are just constants, and q for a given charge will again be a constant. So the only thing that changes the value of the potential due to this point charge is r. And therefore, from this I can say that if a point is at the same distance r from the point charge, then the potential will be constant. So V is constant if R is constant. So for example, if I have a point charge, let's say plus Q, and I try to find out the potential at many different points around this point charge, then I will see that all the points which lie on the same radius R from this point charge, at all these points the potential will be the same because they are all at the same small r distance from the point charge. And then by joining all these points at which the potential is constant, I will get what is known as the equipotential surface. So as I have said, equipotential surface is a surface on which the potential at all points is the same. So for a single point charge, you can see very clearly that the equipotential surface is a concentric spherical surface. It's spherical because here we have just shown it in 2 dimensions, but actually it will be a 3-dimensional object. It will be spherical. It will cover all the points which will lie at the same distance are from the point charge. So for the single point charge, the equipotential surface is a spherical surface centered at the charge. One very important property of an equipotential surface is that equipotential surfaces are normal to the electric field. So the equipotential surface at any point is normal to the electric field at that point. As you can see very clearly, the field is normal to the equipotential surface, and this is actually in general a property of the equipotential surface. Let's just quickly take a look at what the equipotential surface looks like for some other charge configurations. If you have a uniform electric field, let's say a uniform electric field along the x-axis, in such a case the equipotential surfaces are planes which are normal to the x-axis. These planes are, again, because they are equipotential, normal to the field, and they lie along the yz plane, and therefore they are normal to the x-axis. So this is how the equipotential surfaces look like for a uniform electric field which, let's say, is parallel along one particular direction. Similarly, we can take a look at equipotential surfaces for an electric dipole. At every point, as you can see, the electric field will be normal to the equipotential surface. So this is all about equipotential surfaces. So we have seen the expression for electrostatic field, and so far we have been discussing the electrostatic potential. Finally, it's time to say what is the relationship between the electrostatic field and the electrostatic potential. To understand this, let's take 2 points A and B which are placed close to each other, but for clarity we have enlarged this picture. We have 2 points A and B, and the potential values at these 2 points are V and V plus del V. So here you can see that there is a change in the potential in the direction of the electric field. So we see that the potential at A is V plus del V and the potential at B is V. Now what I'm going to do is I'm going to take a unit test positive charge. I'm going to take this unit test positive charge and move it in the direction from B to A. The perpendicular distance between these 2 points is del L. Now when I take this unit test positive charge Q naught from B to A, what I'm essentially doing is doing work against the field, and I want to find out what is the work done to take a unit positive test charge from point B to point A opposite to the direction of the field. Now it's very simple that the work done by me in taking it from B to A will be opposite to the work done by the electric field in taking it from A to B. So instead of writing F external, what I can do is I can write the force due to the electric field, but I will write it with a minus sign. So if I ask you what is the work done in this process, first of all, work done is given by force into displacement. But since it's a unit positive test charge, I know force is Q into E, and Q is simply 1 because it's a unit positive test charge. So the value of F will be the same as the numerical value of the electric field E. Now instead of writing the expression for the external force, I am just finding the force exerted by the field, which is E. And the negative of this will be the force which I have to exert to take this from B to A. So when I'm finding the work done by the field, I see that the value of the force is numerically equal to E, and that multiplied by displacement del L is the work done by the field. To get my work done, I put a minus sign, so the work done by an external force in this process is minus E dot dl, or I can say it is minus E dl simply. Secondly, I want to remind you that work done is nothing but the change in electrostatic potential energy, but UA minus UB is nothing but the potential difference multiplied by the charge, and charge is simply 1 because it's a unit positive test charge. So I get that the work done is nothing but the potential difference VA minus VB, and then I can simply see that the potential difference is V plus del V minus V, which is simply del V. And now because I have two expressions for work done, I will simply equate them and I will get that E is equal to minus del V by del L, and this gives me the relationship between the electric field and the potential. I see that the electric field points always in the direction of maximum decrease of potential. So if you're following the electric field lines, it means that your potential is decreasing. If you go exactly opposite to this line, it means your potential is increasing. Secondly, remember that the magnitude of the electric field is given by the change in the magnitude of the potential per unit displacement as seen from the formula, and you have to do this normally to the equipotential surface at that point. So as you see in the figure, we were going along the x-axis, and as I have just shown you few minutes ago, the equipotential surface would have been normal. So you have to go in a direction which is normal to the equipotential surface at that point. This gives me the relationship between the field and the potential. So finally, let's see what will be the potential energy of a system of charges. Let's say that I have to create this system of charges made up of the charges Q1, Q2 and Q3, and I want to place them at these points A, B and C, which are at a position of R1, R2 and R3. So you can see Q1 is at position R1, Q2 is at position R2 and Q3 is at position R3. And I'm asking, what is the potential energy of a system in which these three charges have been placed, as you can see. So what is the potential energy? To find that, what we have to do is we have to create the system. And when we create the system, we know what is the work done to create the system. And once you have the work done to create the system, all that work done gets stored as the energy of the system. So let's try to create, or we say assemble this system one by one. The first thing I'm going to do is bring the first charge. Now when I'm bringing the first charge, let's say I'm bringing the charge Q1 from infinity, no work is required to be done. Why is that? Because right now, as you can see, there is no other charge in the vicinity. There's no other charge. So when I bring the first charge, it will be just very easy. There will be nothing to stop me from bringing the first charge. So when Q1 comes, it comes smoothly from infinity to the point B, and I can keep that there without doing any work. So the work done in bringing the first charge is always 0, because before that there is nothing to stop that charge from coming at that point. But now what will happen? Now there is a charge in the region. Now in this space there is a charge, that is Q1. And because there is a charge Q1, around Q1 there will be a field. And this charge Q1 will produce a field, and therefore it will produce an electrostatic potential at every single point around it. And therefore, if I try to look at the points near the region of the point C, I will see that even these points now have a potential. There is an electrostatic potential present at these points also. Why? Because of the charge Q1. Now when I try to bring the second charge from infinity to the point C, I will see that it has to be done in the field of Q1. So when you bring the second one, there is already someone present there, and therefore now to bring it from infinity to point C, some work will have to be done. So when you bring Q2 from infinity to point C, the work done will be given by the charge multiplied by the electrostatic potential at that point. As you can see, the electrostatic potential at that point is Vc, and this was caused by the charge Q1. And what we have to do is we have to find the work done. So you simply find this work done by multiplying this Vc with the charge. So we say work done in this step is Q2 into Vc. And this is nothing but 1 upon 4 pi epsilon naught Q1 Q2 upon R12. Here Q2 has come from Q2 Vc, and the remaining is the Vc. So here you see the work done in this step is Q2 multiplied by Vc. Finally, now you have to understand that now this region has two separate charges. One is Q1 and one is Q2, and these two will now create a field at the point A, and therefore the potential at the points around the point A will be due to not just the first charge, that was Q1, but also due to the second charge, that is Q2. And therefore now the potential at point A will be potential due to Q1 plus the potential due to Q2. And now we will say that the work done in bringing the third charge Q3 from infinity to A will be nothing but depending upon the potential due to Q1 and the potential due to Q2 present at that point A due to these two charges. So I will see that the work done in this step, which is nothing but charge into the potential, will be given as Q3 multiplied by VA, and VA is V due to Q1 plus V due to Q2, and therefore you see there are now two terms. And from this I can see that the total work done in assembling these charges was 0 for first one, Q2 Vc for the second one, and Q3 Va for the third one, and this is the total work done, which is simply obtained by adding the work done in each step of the assembly of these three charges. So the first term, that is Q2 Vc, is nothing but 1 upon 4 pi epsilon naught Q1 Q2 upon R12, where R12 is the distance between Q1 and Q2, and the second term is Q3 Va. In this you have two terms each. The first one has R13, which is the distance between the first and the third charge, and the second part of this term has R23, which is the distance between Q3 and Q2. So in total we have three terms, which gives me the total work done in assembling these charges at the given locations. You just add the work done in the different steps, and I get 1 upon 4 pi epsilon naught Q1 Q2 upon R12 plus Q1 Q3 upon R13 upon Q2 Q3 plus R23. So in general, if you want to find the potential energy, that is if you want to find the work done, you simply have to take the charges in pair and divide that by the distance between these two charges and add that all up. And as I told you before, all this work done will be stored inside the system as the potential energy of the system, and therefore we say that this is the total potential energy of the system. So work done in assembling the charges is stored as the potential energy. The order in which this assembly was created does not matter, even if you brought in Q2 first and Q3 later and Q1 last, or in some other way, then also you would get the same final answer. So the next question I want to ask is, what is the potential energy of a charge in a given field? So how is this different from what we did before? We found the potential energy due to a single point charge. How is this question different from that question? It's different because now I'm asking you the potential energy if I place the charge in a given field. So remember, previously what we were doing was that we were bringing a charge in an empty space where there was nothing before the charge. So you were bringing a charge, and because of this charge you were finding the potential at some point. Now what I'm saying is that even before you bring the first charge, there is already some external field present, and therefore the main difference is that we are now concerned with the potential energy of a charge or charges in an external field. When I say external, it means that the field in which it is placed is not created by the charge itself. So we are saying that there is already a field, and in this already present field I bring in a new charge and I ask, what is the potential energy of this charge in an already present field or in an external field? So by definition, the potential at any point is the work done in bringing a unit positive charge from infinity to that point. We have already seen this. So I can say that the work done in bringing a charge from infinity to a point P in the external field will be Q times V, because V is W upon Q. So I get W is equal to Q into V. So remember that work done in bringing a charge from infinity to a point is Q into V. This work done is stored as the potential energy of the charge Q, and therefore finally I say that if the point P has a position vector R relative to some origin, then I can write that the potential energy of Q at a position vector R in an external field is simply Q times VR, where V is a function of R because potential is a function of the position at which you are considering the potential. So VR is the external potential at the point R. So simply speaking, all I'm saying is that the potential at a point in an external field will be given by Q, which is the value of the charge that you will place at that point, multiplied by the potential, and this potential is the potential created due to the external field. So let's then ask the question and try to answer it. What is the potential energy of a system of two charges in an external field? So let's start. Remember, in the previous case, we saw that when we were bringing the first charge, when we were trying to assemble a system of charges, and when we brought the first charge, no work was done. Why? Because there was nothing there before the first charge. However, in this case, it will be slightly different because these two charges are going to be placed in an external field. So already these 2 points which we are considering, already there is an external field. And I'm going to bring in these two charges one by one inside this external field. So now I'm going to say that because of this external field, already there was some potential present at the points A and B, and these potentials which were already present is VR1 and VR2, where R1 and R2 are the position vectors of these points with respect to some convenient origin. So there's already a potential present at these points, and now I say that I will calculate the work done in bringing the charge first Q1 from infinity to the first point A. And when I do that, it will not be 0 this time because already a potential was present at that point, and therefore the work done will be Q1 into VR1 because VR1 was already present. So this is the work done in bringing the first charge. Now, when I want to find out the work done in bringing the second charge, first I have to ask, what is the potential at the point P? Now, point B already had a potential because of that external field, which was VR2, but now because there is a new charge introduced in its surroundings, therefore, because of this new charge, also there will be an addition of the potential at point B. Let's say it is the potential due to the charge Q1, that is VQ1. So the total potential at point B is now VR2, that's due to the external field which was already present, and VQ1 which has come because of this new charge Q1 which we placed in its surroundings. So now if I want to find the work done in bringing Q2 from infinity to this point B, it will simply be Q times multiplied by this whole potential, that is Q times VR2 plus Q times VQ1, which will be QVR2 plus Q1Q2 upon 4 pi epsilon naught R12, where R12 is the distance between Q1 and Q2. So I get that the potential energy of the system, which is nothing but the work done, the total work done in assembling this configuration, is Q1V1 plus Q2V2 plus this term which has arisen because of the interaction of the particles, that is Q1Q2 upon 4 pi epsilon naught R12. This is the total work done, or you can say it is the potential energy of a system of the two charges in an external field. Similarly, I can find the potential energy of a dipole in an already present field, that is the potential energy of a dipole in an external field. Now, we have already seen in the first part of electrostatics that whenever I have a dipole in a uniform electric field, this dipole is not going to experience any net force, but will experience a torque given by P cross E, where P is the electric dipole moment vector and E is the electric field. So, this dipole placed in a uniform electric field will not experience any force but experiences a torque. Now, this torque, what does it do? Whenever you place this electric dipole in an external field, this torque tries to rotate this dipole in such a way that it becomes parallel or anti-parallel to the electric field, which means that there is always a natural torque acting on the electric dipole which is trying to align it with the electric field, this torque. That means if I want to rotate the dipole in a direction opposite to the direction in which the electric field wants to rotate it, it means I'll have to do some external work. That is, an external torque is applied by me in such a way that I have to do work against the torque applied by the electric field. So I say it just neutralizes this torque and I'm going to now rotate it in the opposite direction. Let's say from a starting point of theta naught, that is a random angle theta naught, to some other point theta 1. We will have to do some external work, and this external work is stored inside this electric dipole as the electrostatic potential energy, and this external torque will be nothing but tau external d theta going from theta naught to theta 1. So why have I used the same tau? Because the external torque applied by me has to be equal and opposite to the torque which it was experiencing, and therefore the value is the same, and therefore I've used the same tau, and this will be tau d theta going from theta naught to theta 1. This is somewhat like saying it's force into displacement. So tau is doing the work of force, and here instead of displacement you have angular displacement, that is theta. Tau into d theta going from theta naught to theta 1, that is from one position to the other position, and because tau is a cross product of P and E, I can replace tau with Pe sine theta. So I get integral theta naught to theta 1 as Pe sine theta d theta, and this comes out when you open it out to be Pe cos theta naught minus cos theta 1. So the work done in rotating an electric dipole in a external field is Pe cos theta naught minus cos theta 1, and this work done is stored as the potential energy of the system. And as usual, whenever we were defining a potential energy or a potential, we were defining that one point where the potential was defined to be 0. So in case of an electric dipole, the point, that is the angle of 90 degrees, is considered to be the 0 potential energy point. So we say that the potential energy is taken to be 0 at theta naught equal to 90 degrees. And using this, then I can define the potential energy at some angle. So just like we define the potential energy at a point, in this case I define the potential energy at an angle. So this will be defined by taking the electric dipole from the initial 90 degrees to the angle where you want the potential energy to be found. So instead of saying infinity to a point like we were doing in the normal cases, for this case we will say from 90 degrees to the angle that we want. So the initial angle will be 90, and therefore instead of theta naught it will be pi by 2, and that will just go to 0, and I get u is equal to minus Pe cos theta, which is minus P dot E, and this is the expression for the potential energy of an electric dipole, that is u is equal to minus P dot E. Finally, I want to make one last important observation about the electric field. Whenever you have a charged conductor, we know that the charge on a conductor resides at its surface. But in order to make this charge flow to its surface, some work has to be done. So during the process of charging a conductor, work has to be done to bring the charge on the surface of the conductor, because no charge is allowed to be inside. And therefore, while doing this work, what happens is that because of this work done, energy gets stored around, that is in the space surrounding the conductor, some energy gets stored, that is the electrostatic energy. And this electrostatic energy per unit volume is known as the energy density of a charged conductor. So we say that the work done in moving all the charges to the surface of the conductor gets stored in the electric field surrounding the conductor in the form of electrostatic energy, and this electrostatic energy per unit volume is known as the energy density. And the formula for the energy density, which is nothing but the electrostatic energy per unit volume, is given by half epsilon E square, where epsilon is the relative permittivity of the medium, and that can be written as K into epsilon naught, where K is the dielectric constant. So in general, I will say that the energy density of the electric field of or of a charged conductor is half K epsilon naught E square, where K is the dielectric constant of that medium. So this wraps up all the concepts that I want to discuss with you under the umbrella of electrostatics. This was a huge chapter with a lot of concepts. I hope you enjoyed watching our videos. Thank you for watching. So thank you for watching this video. We take a lot of pains to bring these videos to you. If you like our channel, please click subscribe. And if you want to buy your very own target book, please click on the link given here. Please stay tuned and keep watching.